Go. Hello. Okay, just as I said before, they changed the title and then they changed the room number for us. So welcome, thanks for showing up. I hope that this is the talk that you wanted to be in, and if it's not, we welcome you to. We really look forward to explaining compiling Objective-C using the Visual Studio 2015 C++ code generation technologies that we use to build the company. This will be a joint presentation between the compiler team and the Windows operating system team. My name is Jim Radigan. I'm the dev manager for the CodeGen Technologies team. And that's Solomon. He's from the Windows team. He'll be talking quite a bit about the runtime. They inserted this slide into our talk for us. If you can, scan that and provide feedback. That's the obligatory slide. So the talk is really going to be at a high level about what we think is some cool stuff that we're putting into the code generators that's new for 2015. And then we're going to pull back and we're going to talk about how we're going to use this to create some new developer tools. So my mission is at least to start out and get a few things across. We're going to talk about the new CodeGen technology. We're going to talk about how it's used to build the entire company internally at Microsoft. We're going to talk about how it's used to build all the universal applications for C# now with an ahead-of-time compilation. We're going to talk about how all of this accrues to the 2015 retail products that you'll be able to buy soon. And then we're going to talk, especially Solomon will talk quite a bit about how this accrues to new compilers and languages for Windows. So code generation really, really matters. That's the Intel Pentium right there. That was about 3 million transistors. Now, if you scale the Pentium using that semiconductor process for the big chip that's about 2 years old there, that's what the Pentium would look like in relation to the current Ivy Bridge. And the important point here is that about 60% of that area on that large die is controlled by a code generator. So code generation really matters, and that's why we're going to come at this bottom up. So for code generation, the key things that I want to get across are we're bringing in new security, new secure code generation. We're going to be talking about a new asynchronous programming model. We're going to talk about new auto-vectorization, something that I think is quite revolutionary, new incremental whole program analysis. And then we spent an enormous amount of time listening to you guys about build time. So we're going to talk about a lot of work that we did for basically speeding up the compiler, especially for the developer scenario. So I'm going to jump right into security. This is how a couple of guys in China hacked the Google Gmail client. So I'm going to go through a simulation here, hopefully. So right there at the bottom, what you can see is that we're going to create an event object, and we're going to actually add 2 references to the image object. Both the span and the event object are going to take a reference on that. And then we're going to call F1. Up here, we're going to create a copy, as you can see, but we're going to forget to do an add ref. So right there, the reference count's wrong on image. Right here, we're going to actually free the image object, and we're going to have a dangling pointer. At this point, image is freed, and event is going to go out of scope. And so what you didn't see is that in this step right here, the attackers will actually spray the heap, and what they'll do is they'll write the vtable. Then what we're going to do is set up an asynchronous event here. After event goes out of scope, we're going to have a dangling pointer, which is in E1. And E1 is pointing off to what used to be the image, but its vtable's corrupt. So right here, bang, you're gone. So that's a classic use after free. So what we've done over the last 2 years is try to address that kind of attack and many others. And I tried to think of a slide that would actually get the idea across to you really quickly in one chunk of code, but that's what we originally emitted for checking every indirect function call when we first brought the project up. So what you can see is if the pointer to the function came in an ECX, we'd move it over to EAX, operate on it by using it as an index into a direct map cache. Okay, so that's what that first shift right is. And then there's the table lookup. And then when we're going to go to the table, we're going to pull out a byte, and we're going to see if a bit is set to see whether or not it's OK to call that address. All right? And the reason I titled the slide Chum in the Water is because when we put this out there, we've actually compiled things with this now. It was fully documented on the internet by the bad guys, basically, I think within a half hour, just because they disassemble everything so quickly. Now, that's not the exact code sequence that we emit today, but this will be available to you in the compiler, and I'll explain that in a second. But that is a wake-up call. So this is a picture for how that code operates. This is sort of what the table looks like. The rectangle on the right-hand side for you is the 8 bits that we would pull out once we did the load and shift. And that 1 bit would be covering 8 bytes for a 64-bit address. And that bit would be set by the compiler, the linker, the loader, and the operating system. So in order for this to work, there was a tremendous ripple effect throughout the entire system. We had to modify the Windows Memory Manager in order to make this something that somebody could use in production. This is not an analysis tool. This is something that we recommend to you to use in your production. The loader had to be changed, the OS loader. The linker and the compiler as a pair had to be modified. It was really important for us to be able to guard code that was compiled with our compiler, but still allow you to link with code that was third-party code that was built with another compiler or that was old and was a DLL. And we had to make small binary format changes. And internally, we have a set of tools that will actually crack our binaries, do static analysis. And we had to modify those in order to crack binaries for 4 different target architectures. So the new switch for you guys on the 2015 compiler is going to be /guard. And we did a tremendous amount of work on performance and interop, and we did a massive amount of testing. And this is out there today, now, in Windows 8.1 in certain parts and in Threshold, as you can look up on the internet, undocumented by us, which is hysterical. And it's stopping zero-day exploits now. So moving right along, what I want to talk about is a new asynchronous programming model. It's really important to recognize that Moore's law has come to a halt almost, unless the material science guys come through with some new breakthrough. So you're going to see a lot more multi-cores in the next 2 years. And that's an example of one of the build machines that we use for building Windows. That's a hyper-threaded 80-core machine. So we've introduced a new asynchronous programming model by changing the front end to add 2 new keywords, yield and await. You may have seen this in C#. Our implementation is radically different than what was done in C#. And this is all implemented through the back end being able to generate what we consider to be true coroutines. And we're doing this on all 4 architectures that we're targeting. So what's a coroutine? So there's Fibonacci. And as you can see, we have the new yield statement in there. And I'll show the caller. So there's main. And what you can see is on every iteration of that loop, we call fib. And then fib, on every iteration of that loop, is going to yield A. It's going to set itself down to be resumable. And it's going to be resumable at the next statement after the yield. So on every iteration of main, we're going to actually resume where it says auto next equals A plus B in the coroutine. And I use this example because I wanted to show you this is extremely performant. We spent a lot of time on the design of this to make sure this would be really, really fast. So here it is in slow motion. I tried to do this, rather than show you pseudocode, I did an animation. So if we call fib, G is the generator that we return, we set up RCX and then the argument to fib, which is the number of times we're going to iterate, which is 35. RCX is a pointer to a chunk of storage on the stack for a return value. We're going to set up the return address. Then we're going to set up the registers for fib itself. And RBP is going to point to something that's the stack frame for the coroutine, which I'll show you in a second. So we're going to save the registers before we call, grow the stack, just like you would do a normal call. And now what's going to happen is we're going to create a frame for the coroutine in the heap. And when we do this, we've extended the STL library such that that promise is a customizable data structure for you. You can actually customize that portion of the heap. The bottom part of the heap will be something that the code generator uses for making sure that we interop. So then what would happen is we suspend, and then we save the registers, the call esave registers, and then we get set up, ready to go back into main to resume the program in that loop. And we're back. Now all of that animation for all those registers and creating the stack and going back and forth is all the code that the code generator would emit, and it would be unique for each architecture, for ARM32, x64, and x86. So this, one of the things I think is really important about this is it's super, super scalable. We had some examples on a laptop when we first had this working where we had millions of these things working. And I'll show you a great example. So we think that the cost of resume and suspend is comparable to that of a function call. It enables a zero overhead abstraction over existing asynchronous facilities. I'll show you the example where that matters right here. And if you look, there's a TCP reader written with our await keyword. If you were to try to program this in C++ today with any of the constructs that we have, this would be about 10 times the amount of code. So what happens is that on this particular example, with a loopback, we actually were able to get about 15 gigabits per second. That's how quick this was. So moving right along, some more code generation technology that's new for 2015. We improved the vectorizer. Now we can actually legally vectorize control flow. So in this example on your left, if you look, we're going to be writing to two different left-hand sides in that if-then-else. This is really important because if you want to get the performance of that large die that I showed you in the beginning, you've got to be able to vectorize control flow automatically. So conceptually, what we're going to be able to do here is we're going to create a mask for the condition, duplicated 4 times if this was SSE2, which is 128-bit vectors. And then we're going to generate code that's the equivalent to that. We'll have 2 vector registers, vector 1 and vector 2, and we'll use the mask as shown on the slide. So for the true side, you get values out of the right-hand side, and where the mask was false, you'll use the left-hand side, and then we'll OR those together. And then for the left-hand side too, it's going to be the inverse of that. Now what happens here is we'll be writing back old values into the left-hand side of 1 and the left-hand side of 2. And that doesn't violate the values that were there, but it does violate the C++ coding standard that's new for parallelism, which is that you have to be able to reason about the program sequentially. And so if we're introducing writes, even though we're writing back an old value, that would be illegal. So we have to do the analysis to make sure that it's OK to write back old values and that this is not something that would possibly introduce a race condition. So for those of you who are not familiar with assembly language, that's what we return the Black-Scholes key loop into. This is an incredibly important loop for financial applications. And you can see each of those red statements as some complex control flow. And that's the assembly language, which may look like Klingon to some of you. But the point I want to get across is that that is straight line code. And what's really cool is if you see the one instruction that's right after the red arrow, that instruction was introduced by Intel in the architecture to handle that not mask. If you see the two not masks in there. So the hardware has actually been built for vectorizing control flow. So this has a huge impact. If you look at Black-Scholes, for AVX2, that's a 600% speed up. That's a lot. And it's everywhere. It's very pervasive, of course, to have C++ with control flow. So this is something to look out for. If you can actually twist your code to the left or right to make this hit, it's a big deal. So the next thing I wanted to move on to was for the new code generation technology is Pogo. We introduced Pogo for Xbox. And one of the things that we've seen in some of the early games that we've worked on is 20% speed ups, and people in this industry are really excited for 2 and 3% to get the frame rates up. So this is a really big deal. And one of the things that we learned by working with the Xbox community is that a lot of people really like to, in the development cycle, they like to work with fully optimized, fully Pogoized builds. So it's really important that we come up with systems to help that developer scenario be debuggable and quick, and now I'm going to talk about that in a minute. But that's two great things that fell out of working with the game developers. And that's all in 2015. So now I'm going to talk about compile time and throughput. Now, compile time and throughput is very, very scenario sensitive. There are two different ways to look at it. One is you're a developer, and you're going to do that circle on the left probably 40 times a day, right? I mean, everybody in here has been in that loop endlessly. Then the other one is the build lab scenario, which is just nightly you're doing a giant build. So we've tried to do things for both scenarios. We favored the developer scenario this time for this product release. This is a measurement of what you'll get in 2015 as it applied across the board as an all-up for all of the different things that we did for throughput. The first three are probably all due a lot to speeding up the linker and for speeding up how we generated debug information. And then the compiler itself is something, the build times for the compilers was sped up by doing incremental whole program analysis, which I'll talk about in a second. But that's sort of a way that on one slide I could measure some of the high notes on what we did for throughput. So this is what we did for the compiler that speed up that I just showed you. It's incremental whole program analysis. That's the compiler up on top. That's MS-HTML. Those are where we actually played back the edits that were checked in for the last 6 months and then measured what the compile time speedups would be for the average developer, and it's pretty substantial. That's in 2015. So here's an example of how incremental whole program works. That's a simple function, and whole program analysis would prove that C, A, and B are not overlapping in any way, shape, or form. So we'll go ahead and vectorize that loop, and you get a massive speed up. And that's really cool, but you have to think about it. What if that function is only one of 100,000 functions and you've got 500 files? So there's the call site below. And let's say that on your right-hand side, we make that one edit in gold. So typically what happens with most compilers today is that if it's whole program or link time code generation, which is when you really get the performance, that's where we really get the inlining right, that's where we use the call tree to do a bottom-up global view of the program, that would be a recompile. So you'd recompile 100,000 lines, 100,000 functions across those 500 files. With incremental LTCG, you're only going to compile that one function. And This was really hard to do. There is a trail of failed PhD dissertations on this topic. We have them as the bibliography. So to do this, we actually had to change the workflow for the compiler. Typically, that's what you'll do. We'll actually input CIL, which is an object file that contains an intermediate representation that's not what you think of as object code. It's actually our ASTs. And what we'll do is go through every one of them, build a call graph, then bottom up, we'll compile the whole application. But now what we've done is we've introduced a new workflow. We've got a new PDB format. We call it an incremental PDB. So what we'll do is persist these CIL files and the new PDB format forward to the next time around, and that's what will allow us to do the global analysis really quickly and only compile that one function out of the 100,000. And this will be in 2015. We also sped up the O2 scenario. This was really a pain point for a lot of people. We heard what you had to say. And these are some of the speed ups. This is where we do incremental linking when you're actually linking a lot of static libraries. That's Chrome for an incremental build up on top. That's an enormous speed up for when we build Chrome. And then that's the full build for Chrome on the second row. And then that's Ogre 3D, and Audio 7 was too small to show up. But this is a pretty significant speed up. And then we have a new debug fast link, which is really something people have been screaming for. Basically, the linker spends most of its time generating our PDB files. We have an incredibly rich debugging experience, but to support that, we have to generate pounds of information. And so one of the things that debug fastlink will do is it'll maintain the debug information in the object files rather than move them into one PDB, and we'll actually create a new dictionary PDB to refer back to the different object files. So it's a simple idea. It's basically we don't move 400 pounds of stuff each time we build the application. We just create a lookup for it. And then we had to change DIA, the interface that we publish, for being able to operate on this on all the new formats. So this is the part where I transition the talk. I'm going to start to talk about platform now. So I talked about all the cool technology we're putting in the compilers, and now I'm going to transition into Objective-C. So we compile Windows every day, and we have to map it to the hardware. So the code generator and the linker really is that red arrow. It really, really matters. So the code generators that you're going to get it in 2015 and what you're going to use with Objective-C are the ones that we use to build Windows every day. And it's also used to compile SQL right now, Office, .NET, Visual Studio, and some of the Windows features I think that Solomon will be talking about shortly. Everybody thinks about code generation really straightforward as it's responsible for getting the right instructions, and it's really, really responsible for doing a great job on optimization and register allocation, right? That's what the code generator does. Not many people see that list. When we generate code, the easiest part is getting the switch statement ready for the instruction selection. The hardest part is generating all the code for those 7 other items that I just put up on the screen. The code generator is responsible for unique ABI performance on all the architectures. It's responsible for security. It's responsible for all the complex interop, for all the weird corner cases between managed code, native code, WinRT, you name it. We also are responsible for the runtime semantics so that when we optimize in the presence of exception handling, for example, you get the right values in your finally. We're also responsible for emitting debug information, especially debug information for optimized code. We're worried about getting ref counting right and setting up the GC correctly for .NET. And we're also responsible for a lot of errors and warnings that are sometimes unique for the runtimes. So to make it clear, here's a picture. Everybody's thinking that the code generator is going to create an executable and that's going to run on the hardware, right? Seems straightforward. That's the picture that I look at every day. That's the 7 items that I just showed you. We're going to create an executable that actually runs and interoperates with all of those frameworks, all of those runtimes, and the executive layer of the operating system. So when you start to think about cross-platform, you really have to start to think about it bottom up. It's harder to compile for the platform itself than it is for the chip. We've also extended the code generator in this product cycle to do ahead-of-time compilation for C#. So in this particular example, what I'm showing is that that one code generator is going to generate code and produce an executable that will interop with all of those frameworks and all of those runtimes. Okay? So this gets even more complicated when you crossbar this with the hardware. Sorry, my clicker's slow. I don't know what's happening. So every one of those rectangles there is first compiled by the compiler for the ARM32 ABI. Calling conventions are unique. How we unwind the stack and exception handling is unique for ARM, et cetera. Now what happens is we go back and we compile the executable to interop with the rectangles and squares that we've shown that are unique for ARM. Now, we do that for ARM32, and all of that also has to make sure, all the code we generate also has to make sure that the semantics between these runtimes is correct. So for example, you may have an application that's using ref counting. It's got something in the heap for C++, and you've got .NET code, which has garbage collection. And you take an exception. Now what happens, right? We ask ourselves that a lot, too, when we're in the debugger trying to figure out what went wrong. But we do that for x64 uniquely, as well as x86, ARM32, and a new processor that we're going to be coming out in the fall. Right now, we have code generation for all four of those targets. And so we look at C2 and the linker as part of the ABI for the platform. Now, if you come at cross-platform top-down rather than bottom-up, which you've just seen, you can see that across all these vendors, C++ is a language that spans. But right now, what's going on is for Android and iOS, the front end is Clang. For us, it's our front end that we continue to advance, which has a lot of Microsoft extensions. But there is a slight inductance mismatch between these front ends. So in response to this, what we did is we hooked up Clang to our C2. And we're at a point right now where we've got 82% of our internal testing working. That's a pretty substantial thing for all four architectures that we target. We also have brought up, going deep, a lot of applications that actually test things asynchronously. You can't really feel where you are in the project and predict milestones unless you're doing things like this Bing demo, which actually responds to pings bing.com through a RESTful set of APIs. It has triply nested lambdas. It has exception handling. We've got this working, and it parses and generates code for an enormous number of complex headers. So now, once you have Clang generating code for C++, it also parses Objective-C. So what I'm going to do is go into a part of the talk which allows us to show you the Objective-C compiler, and that'll allow us to transition over to Solomon. So just give me a second here to log in. Okay, so this is my LLVM compiler. I don't think it's very exciting to have you guys watch us compile something. It's like watching paint dry. So I just wanted to show you my LLVM compiler full build there with Clang and C2. And that line on the top there is where I dropped my Clang C2. And this is the elements demo, the periodic chart for the elements that you can see on some websites. And so this is all written in Objective-C. and you can see the performance is pretty good. The colors are great. And what's neat about this is that the application is written in Objective-C. As you can see, as I pull down the projects over there, all those files were compiled by the Visual Studio 2015 code generator. But what's cool is, and I'll show you in a second, is we compiled a whole bunch of other stuff here. So if I go back up, I'm going to enable some breakpoints. And then I'm going to step in. So you can see I'm in main right there where the yellow arrow is. And then I'm going to single step. And now I'm going to step into the application itself, into the UI layer. And as you can see, that's written in Objective-C too. So we compiled the application and we compiled the runtime. And what's really cool is if you go to the call stack here on the compositor thread, and I resume, you can see that the graphics coming from the Objective-C runtime are mapped onto the DX11. So in this particular demo, I've got this hefty 12-pound laptop with a giant NVIDIA graphics card. All the graphics are being mapped onto the NVIDIA card. And then if I go to the breakpoints and I disable that, now I'm going to resume the program. Now those were the elements, so what's really cool here is we're going to create one element in that list, and that's an object. And what I wanted to show you now was the debug information, the symbolic debug information that we emitted. So if you look at the element, which is in that lower left-hand pane, you can see that as I crack the element object, we've got the correct Objective-C type system information in there. It's inheriting the base system NS object. And then if you look, you can crack the NS object itself, and you can see that we have the superclass right and all the ISA information for the class system. So you get a full, rich debugging experience here. You can actually just, if you wanted to just make sure we got the values right, we're going to be cracking, that's the atomic number 89, whatever that maps to. Anybody know that one? So then I'll just disable the breakpoints and just resume. And we're back. And so that was all compiled with the code generator that builds Windows, SQL, Office, and is in Visual Studio 2015. It's compiling Objective-C. And now I just want to turn the talk over to Salman, who's going to talk about the Objective-C runtime. Thank you.
There it is. Can you hear me? Does that work? OK, nice. So thank you, Jim. So hi, everyone. I'm Salman. I am a program manager with the Windows team. Now, my half or my third of the talk isn't going to be quite as technical as Jim's. Rather, what I'm going to do is show you how we took the work that Jim and team have been doing and kind of ran with it and built a bunch of, we think, really cool stuff on top of it. And I'll maybe start that by telling you about a problem we had. So the problem was actually Candy Crush Saga. Well, not the game itself, rather the lack of the game. The game didn't actually exist on Windows Phone until relatively recently. Now, we really wanted it on the platform. King really wanted to put it on the platform, especially as you saw yesterday. They've made this ongoing commitment to bring new titles to Windows Phone. But we really wanted to help them get this onto the platform quite quickly. And one of the ways we were able to do that was by working with them to start with their original source code, as they had written in Objective-C, originally targeting the Apple iOS platform, and then with very, very few code changes, rebuilding and repackaging that code, and then deploying it onto Windows Phone 8 and 8.1. And it went really well. As I'm sure everyone knows, it's a hugely popular game. It's been really well reviewed and performs just great on the Windows platforms. So we figured we had something interesting here. So we did what you do. We gave it a name, and we're calling it Project Islandwood. So what is Project Islandwood? So kind of your one-line takeaway, if you remember nothing else about my kind of half of the talk, is that Project Islandwood lets you write Windows Universal apps using Objective-C. So just by maybe quick show of hands, how many folks in here have done iOS or Objective-C development? OK, so 50%? More than I would have expected at a Windows conference. Nice. So when you make a statement like that, like, we're going to support a new language, that's kind of a broad statement. It really means kind of somewhere between 3 and 4 things, depending on how you're counting. One moment, there we go. So first off, you need a compiler, something that can actually understand the language. And again, thanks to Jim and team, we've got a great compiler with all the great optimizations, security features, interoperability, all that sort of stuff. But then along with that, we are providing you with a great Objective-C runtime. So all your advanced Objective-C features, things like automatic reference counting, blocks, all of those sorts of things, they're just going to work. Then you need APIs. Now, because when you use Project Islandwood, you are, in fact, writing a Windows application, you can freely interoperate with a Windows Universal API surface. You can lean on things like Ink, Cortana, et cetera, et cetera, et cetera. But we really want to make it easy for you to bring any existing code, any existing skills, any existing knowledge you have. So along with that, we offer an iOS compatibility layer. So this is, we'll talk about a bit about that in detail in a bit. But really what this is it's a set of headers, and it's a set of user mode libraries that you link into your application, and they provide source-level compatibility with a fairly reasonable subset of the iOS APIs. And language support and APIs aren't enough. We really want to make this a very good, very productive development experience for you, so we have to have a tooling story. And we think we have a good one, so perhaps that's where we'll start. It's called Visual Studio. Jim showed you a little bit of this earlier, and we'll dive into VS in a second as well. But there are just a few things I'd like to call out. First off, it's not just plain Visual Studio. We've actually added a few things to make it a very good Objective-C development experience. So your syntax highlighting, your auto-completion, your right-click jump to declaration, all of those sorts of features will work. Jim showed you a lot of this, and this is so cool. You have a full debugging experience. You have a proper debugging experience. Stack traces, you can inspect variables, actually dive into objects, breakpoints, the whole 9 yards. And because you are writing a Windows app, you can lean on the Windows APIs, so you're not restricted to calling kind of Objective-C or blessed APIs. You can reach out and call more or less whatever you'd like. And more than that, your Objective-C source files can live in the same project as your VC++ source files or as your C# source files. You don't have to segregate them into different projects and kind of wire them together in some weird, odd way. When you're calling functions across that boundary, you're not having to marshal and demarshal parameters. They're just function calls. And then lastly, if you do have existing projects that you've developed in Xcode, we're providing you some tools to make it super easy and super simple to get started working on those projects. So we're giving you a tool that will, I think I have a slide to this. Yes, I do. That will let you start with your Xcode project. You then wash it through this tool, and then out the other side, you get your Visual Studio solution and your project files. And this actually happens in place, so it's in the same directory. So your 2 project files, Xcode and Visual Studio, you can share the same set of source files. You can share the same assets. You don't have to fork your code, make different copies of assets, relay out your program structure. It all works in place. Now, because I prefer Visual Studio to PowerPoint, we'll actually drop into that for a second. See if this works. There we go. So this is one of our SDK samples. It's a really simple app. It was originally written for the iPhone, as you can tell. So this is actually pulling images off of the Flickr account of one of our developers. So for those of you who have done iOS development, there's actually quite a bit going on here. We're starting with a table view. We're going into a collection view. And then we're dropping into an image view inside a scroll view. And all this is wrapped up inside a navigation controller as well. So we've pulled the images. If I could learn to scroll, it scrolls really well, performs as you would expect. But I sort of take issue with two parts of this application. So first off, it was built for a phone, as you can tell. So I'm not a huge fan of this aspect ratio, considering I'm running on a laptop. And secondly, I'm not a giant fan of this white background behind the smaller images. So what we'll do is quickly dive in and show you how to change both of those things. Let's start with the size of the application. So I'm going to do this in the most naive way possible. I'm just going to give it some hard-coded numbers. And the way this works is our runtime engine, our compositor, looks for this category as part of UI application. And if it exists, it just asks the application, how would you like me to render you? And again, I'm just going to do this really naively and hard code some numbers. But you can do all sorts of clever stuff with it. And then, to change the background, I'm going to drop into my image view controller. Oh, I may want to save that. I'm going to drop into my image view controller. And I'm going to say, scroll view, set background color. And this is not a thinly veiled attempt to show you how our autocomplete works. It actually is. UI color, and I think I want to go with black. Yes, that's going to look better. And that first change I made, because it's sort of a runtime change, when you take this code and you run it on your iOS device, it doesn't know about this category or about these functions. So this is not going to affect the running of the application on the iPhone platform. But if I do want to guard these changes, if I'd like these to only appear when I'm running on Windows, I can wrap them in an ifdef. So you sort of have two sets of, or two types of ways to customize your code, runtime versus compile time. And we'll just do a quick rebuild. And run the app. So that to me looks a lot better on the laptop form factor. And I'll surreptitiously click the subscribe button as we're talking here. And I'll dive into the app. Again, that looks a lot better for a laptop. And I think that background color looks a lot better. And while we were talking, what I did is actually subscribe to the feed. So when it noticed that, in fact, there were new images available as part of his Flickr account, it's pushed a Windows notification to me. Now, I can actually act on that notification. So if I click here, ooh, that's not right. I've now hit a breakpoint. Now, Jim showed you a lot more debugging than I'm going to. But what is maybe worth calling out here is, if you think about what I've done, I've started in Objective-C. I've reached out to a Windows API. I've asked it to do something, in this case, create a toast notification. Then I've acted on that notification. So I've come back from Windows C++ world. I've come back from there into Objective-C world, and then I'm going to take that Windows event, and I'm going to inject it back into my Objective-C run loop. So I'm going to say, on the main thread, when you get a chance, oh, hey, there's some new images available. Oh, right, breakpoint. So when I hit continue, it's going to push me back, or I guess pop me back to the root view controller, which is purely an iOS Objective-C concept. And I see, in fact, OK, there are new photos here. And I can just kind of go to town with those. So it's a relatively simple example. But it is showing that events and concepts can span both worlds. You're not limited to just using iOS APIs or using Objective-C APIs, and your event systems can actually live together, and they can coexist, and they can call each other back and forth, and it all just kind of works. And you get to do it in Visual Studio, which I just think is great. So just a quick recap of a few points. So first off, you are writing a Windows application. So it's not as though, even though that was originally written as a phone app, it's not as though we were running it in some sort of a phone emulation layer with phone Chrome around it. It's a Windows app. And we could build it as a Windows Phone app. We could build it as a Windows Tablet app. I mean, they're really the same thing because it is a Windows universal application. Just as you have some source files that are in C++, you can have other source files that are in Objective-C. And these worlds can work together, but you can, at the same time, continue to use the supported iOS APIs. And again, everyone can call everyone else. You can have the eventing systems integrated and actually interoperate really well. And we also saw that you're not limited to fixed screen sizes. Just because you're bringing code that was originally authored for a phone, that doesn't necessarily mean you're stuck to a phone form factor as you're moving to Windows. And you can actually customize a lot more than this. The runtime is actually pretty intelligent and pretty complicated. It looks at how the app was originally written. It was written for a phone versus a tablet. It was written for a certain version of the operating system, et cetera, et cetera. Then it looks at the environment it's running in. Am I running on a laptop with a physical keyboard attached? Am I running on a small screen phone? Those sorts of things. And it tries to behave really, really intelligently. So it knew that I was running in a laptop context in windowed mode, so not in tablet mode. So it preserved that behavior. But if I was running on a tablet, it would automatically run the app in tablet mode, full screen, with all those sorts of behaviors. But you can hint the runtime. You can override certain behaviors. If it notices that there's a physical keyboard attached, it'll suppress the virtual keyboard coming up, but you can override that. You can say, yes, invoke the virtual keyboard and set it to this language or what have you. Or if there's no physical keyboard attached, you can suppress the virtual keyboard because maybe you want to use audio input or use ink for handwriting recognition. So all these sorts of things you can override, you can customize. You're not really limited to the parameters of the original application. And some things you're going to want to do if you're running on phone hardware especially, things like handling the back button and the menu button. And because we know everyone is going to want to do those, you can plumb this through by the sort of interoperability I showed you, or we just make it really easy for you. You just add this one function, and that gets invoked when the physical back button is pushed. But interestingly enough, in a lot of cases, you don't even have to do that. There is default behavior where if it notices you have a navigation controller and you are somewhere and they hit the back button, we just pop you back to a previous view in that controller. So the upshot or a consequence of all this is you can take your app, you can take your code, even if it's in Objective-C, even if it is using some subset of the iOS APIs, and you can deploy to a lot of devices. You're not limited to form factors. You're not limited to just phones or tablets, but you can really deploy to laptops, surfaces. And because of the work Jim and team have done, you're not limited to CPUs either. You can rebuild your Objective-C code and deploy it on x86, x64, ARM-based devices. All right, so the big question we get is, what APIs do we support? Well, obviously, we support the Windows Universal API surface, but on the iOS end, we don't claim to support everything. We support a very reasonable subset of the iOS APIs, but even those don't track to a particular iOS version. So it's not like we're guaranteeing support for iOS 8 or 6 or what have you APIs. Rather, what we do is we look at what apps and what developers are actually using, and those are the APIs we implement first. Now, as this product continues to exist and go forward, we'll add support for more and more APIs, but that's kind of our process. What are people actually using? How are they actually using them? So what does work really well In broad strokes, these are kind of the areas where we focused on and that work really well today. Things game developers need. So you get out-of-the-box support for OpenGL, OpenAL for your audio playback, sensors like your accelerometer, your gyro, core motion, all of those sorts of things work really well out of the box. Your UI code. This is really important for two reasons. One, this shows up in places you wouldn't really expect. A lot of games use things like core animation for moving sprites around and doing animation of that sort. But the other annoying thing about UI code is it ends up being a 100% rewrite when you're moving across platforms. There's virtually none of that you can preserve. So we've spent a lot of time making sure this just works and is really, really full-featured and really, really performant. Again, the app I just showed you had 4 or 5 different views and controllers, and those just worked out of the box. And then obviously we have an industrial strength Objective-C runtime, so automatic reference counting, blocks, foundation, core foundation, all of those things just work. And the last interesting one is services. Let's talk about those specifically. So our runtime takes iOS concepts and we translate them into Windows concepts. So for example, if your app is using notifications, you are, of course, free to call Windows APIs, including notifications APIs, directly, or you can, for example, continue to use UI local notification. And we back-end that with Windows notification actual implementations. So things are going to appear right. They're going to appear like proper Windows notifications. They're going to populate in the Activity Center. But you do have the option for continuing to use the existing iOS code you have. You lose a little bit of flexibility. You lose quite a bit of flexibility there in that you are tied to their APIs. You can't take advantage of some of the newer notifications features Windows has. David Treadwell showed some this morning where you can have sort of interactive notifications where you can construct complicated UIs, but you can continue to use, for example, UI local notification, among other notification classes. It's a similar story with StoreKit. We actually provide a really great implementation of StoreKit. You can continue to use that. And again, we back-end those with Windows Store transactions. And just the third and final example, say your app wants to load and play a sound or load and render an image, and you're doing that with like NSBundle path for resource. Again, you can continue doing that. We provide implementations of NSBundle such that files and directories are all in the right place. And if they aren't, we can remap paths and sort of find everything correctly. And we're pretty confident this approach works because we didn't just work with King to help them bring over their game per se, like just the game mechanics and the graphics and all that. But for those of you who have played Candy Crush or who are sitting in the back playing it right now, it's actually a fairly complicated app. It's got Facebook integration, it's got in-app purchase, it's got notifications, and all of those were plumbed through via the sort of interop layer I just talked about. So what's next? How do you get your hands on this? We'll be rolling out the SDK over the summer. It's in limited release right now. We'll be adding more and more people as the summer rolls on. You are more than welcome, and you are invited to sign up to keep informed. I know the website was having a couple of issues yesterday. I do apologize for that. They've all been hammered out. You can sign up now, and it'll work, I promise. And you are more than welcome to visit our booth. I'm there along with one of our developers, and we're happy to answer any of your questions. And with that, I think Jim and I will be more than happy to take your questions here. Oh, we are going to ask that you come up to the mic because I think this is being broadcast.
Hello. So if you want to take advantage of all the code that's been written in Objective-C, but you still want like
I'm sorry, can you speak up a bit?
Yeah. If you want to take advantage of all the code that you've written in Objective-C, but you want a more native Windows Phone look and feel, are there thoughts on the best way of doing that so it doesn't look like an iPhone app?
Yeah. So UIKit, which is Apple's framework for drawing buttons and scroll views and tables and all that, actually gives you the ability to theme all your controls, so you can set the colors and set the borders and all that sort of stuff. But the default look and feel of the applications, when they're running on Windows, we can actually theme those as well. So if you saw the default font in my navigation controller, that's not the same font Apple uses, which is a really easy change for me to make, and that's the sort of thing we can do by default, so that'll require no work on your side. And that includes things like the background color. It doesn't have to be white. We can change the defaults. We can change the acceleration parameters for scrolling, all that sort of stuff. Yes? Yeah.
Is there any thought given to how to handle apps that are currently using native libraries? And I'm thinking things like VoIP codecs, that kind of thing, currently built into the app. Is there a standard process for mouse holding those through to native Windows codecs, or what would the process be? Yeah, so with that's a wonderful question. So with third-party libraries, there's kind of two approaches you can take. So first off, if you do have source code to that library, it's really simple. You just add it to your project and then build it along with the rest of your Objective-C source. And largely, those will just work. If you don't have source to it, then you can always link your application against the Windows version of that library. And because we do have interoperability between Objective-C and C++ today, C# very shortly, you can just call the Windows incarnations of those libraries. Assuming the interaction models are the same, but yeah, okay.
Yeah, so for some of them, we're actually providing shim layers where we fix or mitigate that impedance mismatch. So, yes?
Back to the beginning of the talk, there was this new feature introduced about coroutines. Have you actually submitted that for standardization to the C++ Standards Committee?
Yeah, actually, the process for that already started. There was a meeting at UIUC, and I think it was accepted for the going to the next steps. This is something that's on the train for C++ 17, but we're shipping this regardless of the standardization, and we'll probably have to tweak it for whatever comes up. I think the standardization is going to get unified, especially around how the libraries allow the user to customize the frame and what we call the promise. Thanks.
Yes.
First of all, thank you. And I found my button. Thank you, first of all. This is great. Second of all, a lot of us iOS developers don't use Objective-C hardly anymore because of the Swift revolution, if you will. What is the plans for adopting Swift into this as well?
We're going there. It's just a day at a time. This is all preliminary. We're going to be struggling to get this out in time in the fall with VS Update 1, but that's just as doable.
I think what Jim meant to say is we're not making any comment on Swift today.
I can neither confirm or deny that
All right, sorry.
Hello. My first question was Swift. My second question is, do you have support for storyboards and auto layouting?
Yeah, so we can load storyboards. We can load nib files. Yes.
And auto layouting?
Sorry.
Auto layout?
Auto lay. Oh, yes. Yeah. So like constraints and all that. Yes. Yes. Yes.
So for all the UI kit stuff that you've implemented, is that backed by Windows XAML controls, and is it using direct manipulation, things like that, to have the right input, scrolling fields, things like that?
No. It's directly on top of DX.
Okay.
So we're not.
Separate implementation from.
Yes.
The other
It's part of a XAML window, so you can sort of make them work together, but they are more or less in separate rects.
Is he using dminit for off-thread scrolling and stuff like that, or?
I don't know. I'll get back to you.
Okay.
Hi. Can you expand further about C# interrupt, particularly like can you bootstrap in C# and then interrupt with Objective-C and the other around?
That feature is still in development, so we're not particularly talking about that today. C++ interop works great. Stay tuned, sign up to the thing, and we'll have a lot more documentation on it. I think we have a really great strategy, and it seems to work really well, but it's not hammered out yet.
Cool, perfect, because we're looking at use cases like in creating C# program, but using UI kit and things like that with Xamarin that enables that play. So obviously that would be interesting to see coming.
So we're talking about, for Project N, the ahead-of-time compilation, we're talking about actually implementing that probably when I go back. But we're talking, so remember the talk was about, it had two parts. One is what you're going to be able to buy right away out of the box from 2015. And the other part is what we're doing with that technology, probably for about the VS Update 1 timeframe. So the Objective-C is post VS 2015, 1 quarter after.
Perfect. Exciting, thanks.
When we develop iOS apps, we often use some third-party libraries. Yeah. After we convert our iOS project to Visual Studio project. Yeah. Where those third-party libraries will work. Okay, such as Share SDK or Location SDK.
Yeah, so the answer with third-party libraries is that you either have to build them from source with your application, or either you have to make sufficient changes so that it'll interoperate with the Windows version of that library, or in some cases we will provide shim layers such that you can keep using the sort of iOS interface, but we'll shim them over to the Windows version of that library.
Oh, thank you.
Sure.
Just a question about the day-to-day workflow. If we have some developers still using Xcode to make a project change, does that mean the people that might be also using Visual Studio would need to rerun the tool or make a separate manual change to the solution? Is it, I guess, is it kind of watching for project changes that might occur to the original Xcode project file?
I think the meta question you're asking is, can you go from Visual Studio back to Xcode? And the answer is no. So the tool is kind of one way. So your project has to exist in some canonical form somewhere. And if you're using CMake or something like that, then CMake can generate MS Build just as well as it can make files. So that can be your kind of one canonical project definition.
Right.
But once it's in Visual Studio, it's perfectly comfortable to stay there, but we don't really go the other way.
So the source files are obviously shared, but the project definition is not.
The source files are shared. Things like your macro definitions, all of that, your paths, those are all imported, your header maps and all that. But no, it doesn't go the other way.
That's a good question, though. There's no reason why it couldn't.
I like the way.
We haven't done it. We haven't done it yet. But
I like the way he thinks.
that's actually, I think that's something we're going to work on. Don't you think?
Just a quick question for the staff. Can we turn his mic off?
Program manager, developer, sorry.
So we're technically over time. I'll maybe take one more question, just not to be rude, but I think we're done at this point. Again, I'm still here. I'll be at our booth on the second floor. Jim's at his booth right here on the third floor.
Okay. So the advancements you made to the Visual Studio 2015 compiler, they're really great for C++. So are all those optimizations for the apps, or all those compiler optimizations also valid for the drivers? Like if I compile with the WDK and stuff.
Those optimizations that I showed, and the optimizations, like for example, vectorization, et cetera, are all on by default. Some of the ones we allow you to opt into, but if they're available for whether you're building Windows or whether you're building an application. And
also, what's the story on ARM64 for that?
I'm already in trouble, so I can't talk about that one. There is, well, I'll leave it to him.
Okay.
We're not making any comments about.
Okay, I'll catch you outside then.
All right.
All right, thank you all for coming.
Thank you.